Welcome. So in this video we'll study about the chemical equilibria. Chemical equilibria. So we know that there are two types of reaction. One is called as the irreversible reaction, like A plus B gives you C plus D. This is called irreversible reaction. Irreversible reaction, and the other type of reaction where the reaction is occurring in both the direction, that is forward and the backward direction, and is called as the reversible reaction. So this reaction is known as the reversible reaction. Now the concept of chemical equilibria is associated with that reversible reaction only. So in this reaction, initially what is happening is that rate of forward direction is more as compared to the rate of backward direction, but there occurs a point at which the rate of forward direction becomes equal to the rate of the backward direction. Okay, we say denote it by the reversible sign like this. So the rate of forward direction becomes equal to the rate of the backward direction, and at this stage what happens is that the concentration of the reactants and products become constants. So your concentration of reactant and product won't change when the reaction will reach the equilibrium. The concentration of the reactants and products won't change. Another point to be remembered here is that reaction is dynamic. So it is not that reaction is not happening. It is happening. It is occurring. But since the rate of forward direction is equal to the rate of backward direction, there is no progress. No progress. Okay, so reaction is dynamic, but there is no progress which is happening. Now other point which we want to cover is that we have catalyst. So catalyst is having no effect on the equilibrium. So the point at which the equilibrium is reaching before using the catalyst will be the same when you are using the catalyst. Catalyst will have no change on the equilibrium point, but only thing is that equilibrium will reach sooner. Equilibrium will reach sooner, since the catalyst will increase the forward reaction with the same instant as that is increased in the backward direction. So the rate of product formation and the rate of reactant formation will be increased to equal extent. So the equilibrium will reach sooner, but it will reach at the same point as it was happening when the catalyst was not being used. So there is no effect of catalyst on the equilibrium reaction. Let us now see the concept of equilibrium constant. Equilibrium constant. Now say we have a reaction which is in equilibrium. Say A plus BB gives you CC plus DD. Okay, this is the reaction, and we know that for reaction to be in equilibrium, rate of forward reaction becomes equal to the rate of backward reaction. Now rate of forward reaction is given by rate of forward reaction is equal to Kf A power A B power B. Okay, rate of backward reaction is written as A equal to KB or B equal to the KB C power C and D power D. Okay, now since we know that for RF is equal to RP, so if we put both of the values here, that Kf A power A B power B is equal to KB C power C D power D. Now if rearrange, it will be like this: Kf by KB equal to C power C D power D divided by A power A B power B, and this is equal to the equilibrium constant, that Kf by Kb equal to the C power C. So this is the equilibrium constant, and why it is a constant? Because at when the equilibrium will be, the concentration of the reactants and products will become constant. So therefore this whole expression will be constant. So this whole expression is known as the equilibrium constant. Okay, now this, if you want to express this, if all are in gases, say this is also gas, C is also gas, D is also gas, then this type of equilibrium is known as the homogeneous equilibrium. And then if this if the reactants and products either of them are gas also, that if the solids are also involved, the liquid also involved, then the equilibrium which will be released, that will be known as the heterogeneous equilibrium. Now we can express the equilibrium constant in terms of concentration. So the way we expressed, we can also express the equilibrium constant in terms of pressure, that is Kp equal to the here we can write pressure of C C, partial pressure of D to the power D divided by partial pressure of A to the power A and partial pressure of B to the power B. This means that partial pressure of A means that how the pressure which is exerted by A on the walls of the container when all the gases are placed in a container. The pressure which is generated individually by A or individually by B is called partial pressure of B, and then individually by C it is called partial pressure of C, and then similarly partial pressure individually by D is called the partial pressure of D. So this way we can express, and then we also know that Kp is equal to Kc RT power delta Ng. So this way we can prove this also. So we know that P equal to CRT, whereby universal gas law we can write here Kp is equal to, here Pc we can write CRT की power C, and here it would be C only, and then here PD we can write as D RT power D divided by here we can write the A power A RT power A into B power B RT power B. Okay, now this will be equal to the C power C D power D divided by A power A into B power B into RT power delta Ng. Delta Ng means that if all are in gaseous state, and delta N means C plus D minus A plus B as is coming from this formula. So this will be equal to the Kc, this expression nothing but the Kc, and then this RT power delta Ng. So this way Kp equal to Kc RT power delta Ng. So this is the relation between the Kp and Kc. Okay, now we can see the units also. If you want to drive what is the unit of equilibrium constant, if you want to calculate that also we can calculate. So unit will be equal to the unit of concentration. So whatever unit of concentration we are using, 12 to the power delta N. Similarly delta Ng if all are gases, and pressure, if whatever unit of pressure we are taking, that is pressure to the power delta N. Okay, so for example we say we have a equation like H2 plus I2 gives you 2HI. This is also gas, this is also gas, this is also gas. Now if you want to write Kp value for this, Kp value is equal to the PHI to the square divided by PH2 PI2. Okay, and now if we all are in atmosphere, this will become atmosphere square divided by atmosphere into atmosphere. This will equal to unitless, so it won't be having any unit. Now you take another reaction, say Haber process, N2 plus 3H2 gives you 2NH3. Somebody asks you write the unit of Kp also and write the unit of Kc also. So how will you write? So if you want to write Kp is equal to the unit of pressure, that is atmosphere, my the delta, and delta means that 2 minus 4 here in this case. So atmosphere minus 2 will be the unit. And if you want to write the unit of Kc, that will be equal to the molar, say all are in molar, so molar power or mole per liter power 2 minus 4, that is equal to molar minus 2. So this will be the unit of Kc. So this way we can calculate the unit of Kp and Kc as well. Let's see a case of heterogeneous equilibria also. So we see a case of heterogeneous equilibria also. Say we have a reaction, say calcium oxide, this is solid, plus carbon dioxide gas gives you calcium carbonate, that is solid. Now for this reaction, if you want to write the equilibrium constant, that is Kc, Kc is equal to the here calcium carbonate to the concentration divided by carbon dioxide into calcium oxide concentration. Now since this is solid, so this concentration will be constant. Even if the reaction is in equilibrium or not, this reaction will be, this calcium carbonate concentration will be constant. Similarly, this calcium oxide is a solid, so this concentration will also be constant. So it will be rearranged and rewritten as Kc is equal to the 1 by carbon dioxide E concentration. So this is the expression of equilibrium constant for this reaction. Now this case of heterogeneous equilibria. So whenever a reactant or a product is in solid, so since the solid concentration won't change, irrespective of whether the reaction has reached equilibrium or not, the concentration of the any solid reactant or product can be taken as 1. Okay, so just simply to tell you that in case of heterogeneous equilibria, we take the concentration of the reactant or product solid as 1. Okay, now let us see a concept of Le Chatelier principle also. Le Chatelier principle. So we know that when any reaction which is in equilibrium and we disturb the equilibrium, say if we have a reaction and we disturb the equilibrium by changing either the concentration or temperature or pressure. Say we have a reaction, say we have A plus B gives C plus energy. Okay, or say we have energy A plus, this is an equilibrium, we have to measure, right? A plus B gives you C plus DD. This is a reaction, and then here say here in this direction is energy released. Okay, now this reaction is in equilibrium, and since the reaction is in equilibrium, this reaction will never end if we are we are not changing the reaction, we are not disturbing the reaction. This reaction will never end. So if we want that the reaction is completed and we want that more product formation is there, and that the reaction is completed, then we have to disturb this equilibrium. हमें इस equilibrium को disturb करना पड़ेगा ताकि हमारे पास ज़्यादा से ज़्यादा प्रोडक्ट बने और रिएक्टेंट का फॉर्मेशन कम हो, यानी कि फॉरवर्ड का रिएक्शन रेट का जो है वो बढ़ जाए और जो बैकवर्ड रिएक्शन का जो रेट है वो कम हो जाए. तो हम उस कंडीशन को हम कहेंगे फेवरेबल कंडीशन ऑफ दिस रिएक्शन. फेवरेबल, सो फेवरेबल कंडीशन का क्या मतलब है? वो कंडीशन जिसपे जो है आपके प्रोडक्ट फॉर्मेशन जो है वो ज़्यादा हो रही है और रिएक्टेंट फॉर्मेशन कम हो रहे हैं, ताकि जो है रिएक्शन को कंप्लीट कराया जा सके और हम चाहते हैं कि जो हमारे प्रोडक्ट फॉर्मेशन है वो ज़्यादा हो. ठीक है, तो हमारा ली चैटेलियर प्रिंसिपल क्या कहता है कि इफ वी हैव ए रिएक्शन इन इक्विलिब्रियम एंड वी डिस्टर्बिंग द इक्विलिब्रियम बाय चेंजिंग आइदर द कंसंट्रेशन और टेम्परेचर और प्रेशर, देन द इक्विलिब्रियम विल शिफ्ट इन ए डायरेक्शन सो एज टू मिनिमाइज द इफेक्ट ऑफ चेंज और नलीफाई द इफेक्ट ऑफ चेंज. अगर कोई रिएक्शन इक्विलिब्रियम में है और हम उसको डिस्टर्ब करते हैं बाय कंसंट्रेशन चेंज करके, टेम्परेचर चेंज करके, प्रेशर चेंज करके, तो रिएक्शन जो है अपने आप को इस डायरेक्शन में शिफ्ट करेगी, फॉरवर्ड या बैकवर्ड डायरेक्शन में शिफ्ट करेगी, ताकि जो हमने जो चेंज किया है उसको इफेक्ट किया जा सके, तो नलीफाई किया जा सके या मिनिमाइज किया जा सके. सो आई एम अगेन रिपीटिंग, लीच प्रिंसिपल इज दैट इफ ए रिएक्शन इज इन इक्विलिब्रियम एंड वी डिस्टर्ब द इक्विलिब्रियम बाय चेंजिंग द कंसंट्रेशन, टेम्परेचर और प्रेशर, देन द रिएक्शन विल शिफ्ट इन ए डायरेक्शन सो एज टू मिनिमाइज और nullify the effect of change. We can so that the effect of change can be minimized or nullified. Okay, now this is our Le Chatelier principle, and we will understand it with some examples. Say if we have a reaction, first reaction, say A plus B gives C plus energy. Okay, now if we are changing the concentration of say A, then the reaction will forward in as per the Le Chatelier, the reaction will shift in the forward direction. That is the favorable state. So increasing the concentration of A is favorable, B is favorable, and if you are increasing the concentration of C, that is not favorable. So if you are removing the C as the C formation is happening and you are removing C from the system, then obviously the reaction will move toward the forward direction, and that is a favorable state. So low concentration of C and the high concentration of A and B, that is the favorable reaction of this reaction. Now coming to the pressure, so if you are increasing the pressure for this reaction, then obviously the reaction will shift in the forward direction where the molecules are decreasing, so the reaction will be in the forward direction. So high pressure is the favorable condition for this reaction, high pressure. And what about the temperature? So since this is the exothermic reaction, so like energy is already removed, so for this reaction low temperature will be the favorite. लो टेम्परेचर, ठीक है। सो एंडोथर्मिक रिएक्शन को हमें एनर्जी की रिक्वायरमेंट होती है, तो फेवरेबल कंडीशन एंडोथर्मिक रिएक्शन के लिए मोर एनर्जी है, और एक्सोथर्मिक रिएक्शन में एनर्जी रिलीज होती है, तो हमें एनर्जी को निकालना होता है, कम टेम्परेचर होता है उसकी फेवरेबल कंडीशन से। सिंपल वे में हम इस तरह से समझेंगे, ठीक है। तो अगेन इफ यू अगेन आई एम रिपीटिंग दैट द कंसेप्ट ऑफ लीच प्रिंसिपल, वी हैव टू डिटरमाइन द फेवरेबल कंडीशन एट विच द more product formation is there and more or less reactant formation is there. So in a reaction, if reaction is equilibrium, we distinct the reaction, that we are disturbing it by changing the concentration of any reactant or product on temperature or pressure, and then we'll see that the reaction will adjust itself in such a way that so that to minimize or nullify the effect of change. Say we have taken another case, and that is the Haber process is there, and 2 plus 3s2 gives you 2ns3 plus energy. So if somebody asks you what is the favorable state for this reaction, so I will say that low temperature, and obviously that if you are increasing the concentration of nitrogen, that is favorable condition. Increase the concentration of hydrogen, that is a favorable reaction, will proceed in the forward direction. And if you are removing the ammonia from the system, then also the reaction will be in the forward state. Then whether high pressure or low pressure, so we will say that the pressure, if increasing the pressure, then the reaction will be shifting in the forward direction. So we will say that high pressure is the favorable condition for this. Okay, so low temperature and high pressure is the favorable condition for this, and under which at which the more formation of ammonia will take place, which will require in Haber's process. Okay, so let's see another example. Say we have PCl5, we are giving it heat, then we have a PCl3 plus Cl2, that is chlorine gas. All these are gases. So now what will be the favorable condition for this? This is a clip of phosphorus pentachloride is there, and then this is a solid, this is also a solid, and this is a gas. So if somebody asks what is the favorable condition for this reaction, favorable condition is that obviously high temperature and low pressure, because if increasing the pressure, then the reaction will shifting, because in this side the molecules are decreasing, so your pressure will, if you are increasing the pressure, and then the reaction will shift in the backward direction. So low pressure is favorable for this reaction, and obviously if you increase the concentration of PCl5, then obviously the reaction will follow the forward direction, and if you are removing the reactants from the system, then obviously the reaction will proceed for the forward direction. So then see, take another example. We have 2HI. If you heat it, then you will have H2 plus I2. Okay, now the favorable condition for this reaction is high temperature, because this is endothermic reaction, and then pressure, there is no effect of pressure, because the number of molecules in the reactants is equal to the number of molecules in the product, so there will be no effect of pressure on this reaction. Okay, so high temperature, no effect of pressure. So in this way we can determine the favorable condition for any reaction at which we can have the more of the product formation, and this is the application of Leach-Atelier principle. So here, just to tell you that here PCl5 is also gas, and PCl3 is also a gas, so all the three are gases. This means that this reaction is example of so here always we have to take equilibrium direction like this. So this is an example of homogeneous equilibria, and all the three are the example of homogeneous equilibria in which all the reactants and the products are in the gaseous form. तो चलिए देखिए हम आयनिक इक्विलिब्रिया देख लेते हैं. आयनिक इक्विलिब्रिया, यहाँ पे लिखा है आयनिक इक्विलिब्रिया. तो आयनिक इक्विलिब्रिया का मतलब है इक्विलिब्रियम इन इलेक्ट्रोलाइटिक सॉल्यूशंस. तो पहले हमें ये बताना चाहिए कि इलेक्ट्रोलाइट्स होते क्या. तो इलेक्ट्रोलाइट्स आर दोज कंपाउंड्स व्हिच गेट डिसोसिएटेड इनटू आयंस इन द सॉल्यूशन. इलेक्ट्रोलाइट्स वो कंपाउंड होते हैं वो जो कि आयंस में डिसोसिएट होते हैं सॉल्यूशन के अंदर. तो इलेक्ट्रोलाइट्स को दो कैटेगरी में बांट सकते हैं, स्ट्रॉन्ग और वीक. स्ट्रॉन्ग इलेक्ट्रोलाइट्स आर दोज electrolytes which get completely dissociated into the solution. Weak electrolyte are those electrolytes which dissociated to a small extent in the solution, to a very small extent, say 1%, 2%, 3%, so not to that much level. So their dissociated to a very small extent. So if we talk about the strong electrolytes, so salts are generally considered as to be strong only. So we can categorize as strong acid HCl get completely dissociated in the solution. HNO3, H2SO4, phosphoric acid, these are the strong electrolytes, they get completely dissociated in the solution. Only base we are having NaOH, KOH, so these also get completely dissociated into the solution. Example of weak electrolytes are weak acids include the acetic acid, HCN, hydrogen cyanide, that carbonic acid, that's 3CO3. All these are the weak acid. Only examples of weak base are ammonium hydroxide, calcium hydroxide, zinc hydroxide, ammonium hydroxide. So these are the examples of the weak base. Now there is a term which is known as degree of dissociation. But the meaning of degree of dissociation means fraction or percentage of electrodes that get dissociated in the solution. So we know that weak electrodes are not dissociated, to a very small extent, that is a fraction or percentage of the compound which will get dissociated into wine. So a degree of dissociation means what percentage or what fraction of the electrode that get dissociated in the solution, that is known as the degree of dissociation, that is denoted by alpha. Here it is alpha. So if 1 mole of compound is there, say 1 mole of acetic acid, you dissolve in solution, say alpha, out of 1 alpha dissociated. Also if 2 moles are there, 2 alpha will get dissociated. If C mole is there, then C alpha mole will get dissociated. So C alpha mole will get dissociated if the C moles of acetic acid get dissolved in the solution. So we take an example like we have acetic acid here, and acetic equilibrium, we have this is the reaction in equilibrium, and we have acetate ion formation, and so the hydrogen ion formation is there. So this reaction can also be expressed in this way also. So we know that when H plus is there in the solution, they get combined with the HO minus. So we have water molecule also, and then we will have production of hydronium ions. So here hydronium is also there. So hydronium ions, this H plus when combined with water in the solution get converted to hydronium ions. So we can write H plus hydronium also in the case of in replace of the H plus sign. Now say when the reaction has started, the initial concentration of acetic acid C, and since the products have not been formed, so concentration will be 0, 0. Now say C alpha mole, that alpha mole alpha of the total compound, that is C, has been dissociated. So at equilibrium, when the equilibrium will be reached, then we have C alpha mole of acetate ion and C alpha mole of H plus ion. And here since C alpha has been dissociated, so C minus C alpha will be the concentration of the acetic acid at equilibrium. At equilibrium, we will have C alpha moles of acetate ion and C alpha mole of H plus ion, and C minus C alpha of the acetic acid will remain. Now if you want to write the equilibrium constant reaction for this reaction, equilibrium constant, then it will be C square alpha square divided by C 1 minus alpha. C 1 minus alpha. So here C will get goes to C, and then we have 1 minus alpha will get detected, and we have C alpha square, then alpha is equal to the K by C ka root. So this is called the Oswald dilution law. So this is degree of dissociation is inversely proportional to the concentration, and so this is nothing but the Oswald dilution. So if we are increasing the dilution, this indicates that this indicate that if we are increasing the dilution, then the degree of dissociation of the weak acid in the solution will increase. So we can write here is degree of dissociation is inversely proportional to the concentration ka square root, and also we can also write it in the directly proportional to this dilution ka square root. So if we are increasing the dilution of any solution, then the degree of association increases. Say earlier it was 2%, and then if you are increasing the dilution, it will go to 3% or say 4%. Likewise, this is the meaning. So this is the Oswald dilution law. So we can derive the Oswald dilution law from this equation. Alpha is equal to K by C. So here we can write this is acid. So this is, we can write in dissociation constant of any acid. Now since acetic acid is a weak acid, it dissociates to a small extent. If we compare it with HCl, which dissociate to complete, which get completely dissociated in the solution, we will see that the K value of this will be HCl will be higher, and acetic acid will be lower. Why? Because H plus formation will be higher and Cl minus formation will be higher in case of HCl, because it's strong electrolyte, where in weak electrolyte, because there is less number of acetate and hydrogen ion will be there in the solution, so value of Ka will be lower. So this is the significance of dissociation constant for acid. Now dissociation higher the dissociation constant of any acid, more is the strength of that particular acid. So this is the significance of dissociation constant for acid. So higher is the dissociation constant for any acid, the higher will be its strength. Acidic strength will be higher. Why? Because that more number of molecules get dissociated if it is a strong electrolyte, strong acid. Now, if we see what are the factors on which degree of dissociation depends, first dilution concentration, as well I already told you, that is Ostwald dilution law. So as you increase the dilution of the solution, the dissociation of the weak acid in the solution increases. This is nothing but the Ostwald dilution law. So concentration and dilution, as I told you, that DOD, that is the degree of dissociation, directly proportional to the root of dilution, and is inversely proportional to the root of concentration. Okay, and then the second item is common end effect. Common end effect का क्या मतलब होता है? So if we have a say we have a weak acid that is dissociated to a very low extent, so H and H plus, and this dissociating to a very low extent. And now if you bring HCl also, you add HCl in the solution, then you will see that HCl will get dissociated to completely, that H plus and Cl minus will be there. And this, since this common ion is there, H plus here is common, here it is common. By Leach-Eterle principle, if you are increasing the concentration of any product or the reactant, then reaction will shift in that direction so as to minimize the effect of the change or to nullify the effect of change. That we know, that is the Leach-Eterle principle. So it is here later a Leach-Eterle principle. So reaction will shift in the backward direction. So this means that dissociation of the weak acid will still decrease. Already it was less, so it will still, dissociation will decrease. So more dissociation will decrease of this acetic acid to still will decrease. Earlier it was lower, so it will decrease to more, because if you are adding the strong chain strong acid in this, then H plus ion will decrease, because the common ion the reaction will move toward the backward side as per the Leach-Eterle principle, and dissociation of this weak acid will decrease. So we can understand this example by considering example. Say there is a shop which is selling the sweets, and that sweets are very already the quality of the sweets is very bad, and only few people are coming to purchase the sweets. And then in nearby this shop, another shop opens which is selling, which is preparing the sweet to an of giving the sweet of excellent quality. Then obviously the people, those who are coming to the previous shop, the one which is selling the bad quality sweet, those people will also move towards the another shop which is selling the good quality. So this way the sale of the bad quality shop will again will be decrease. So by this example we can understand it. अगर मान लो हमारे पास एक हलवाई है, हलवाई की दुकान खुली हुई है जिसकी मान लो जलेबी है, जलेबी जो है बहुत ही ख़राब क्वालिटी की बनाता है, उसको 2-3 लोग ही जाते हैं। तो होता क्या है, जैसे मान लो उसके बगल में ही एक अच्छी जलेबी बनाने वाली दुकान खुल जाती है, तो वो जो 2-3 जो बगल में स्वीट्स जो जलेबी ले रहे थे, अब वो उससे वो भी लेना बंद कर देंगे, और वो जो है जो नई शॉप खुली है जहाँ पे अच्छी स्वीट बनती है, वो वहीं पे ही ख़रीदना चाहेंगे। तो इसका मतलब क्या हुआ कि जो कॉमन आयन की वजह से जो है डिग्री ऑफ डिसोसिएशन जो है वो कम हो गई। और इसमें कॉमन आयन का होना जरूरी है। अगर मान लो जलेबी की दुकान की जगह मान लो कोई जूते की दुकान खुल जाती है, तो उससे जलेबी की दुकान पर कोई फ़र्क नहीं पड़ेगा। तो यानी कॉमन आयन का होना, दोनों को जलेबी ही सेल करनी है इस केस में, यानी दोनों कॉमन आयन होना चाहिए, तभी जो है आपका वीक एसिड का जो डिसोसिएशन है वो कम होगा। एक और एग्जांपल देख लेते हैं। मान लो हमारे पास एक एसिटिक एसिड है, उसने एसिटेट आयन दिया और H+ दिया ना, क्योंकि ये वीक इलेक्ट्रोलाइट है तो डिसोसिएट टू ए स्मॉल इंस्टेंट, एंड व्हेन यू आर ब्रिंगिंग द स्ट्रॉन्ग इलेक्ट्रोलाइट, सो सोडियम एसिटेट इन द सॉल्यूशन, देन यू विल हैव एसिटेट आयन एंड द सोडियम आयन। सो बिकॉज ऑफ दिस एसिटेट आयन इज कॉमन, सो दैट by Leach-Eterle principle it will shift, the direction will shift to the backward side, and the dissociation of weak acid, this H3COH will decrease to a lower extent. So this is the meaning of common ion effect, because the common ion is here, so the dissociation of weak acid decreases, and this is the one factor which affects the degree of dissociation of any weak electrolyte. Then third point is temperature. Obviously if you increase the temperature, then slight increase will be there in the dissociation of the weak electrolyte. Say earlier the dissociation was 2%, now it will if you increase the temperature it may go to 3 to 4%. So dissociation will increase if you are increasing the because obviously the kinetic energy of the ions will increase, and that energy which is required to dissociate the acid into its corresponding ions will be available, and then the dissociation will increase, and then the degree of dissociation will increase. So these are the factors on which the degree of dissociation depends.